All right, this next topic is on conditional statements and inductive deductive reasoning. I really like starting with this quote. The force of logic comes from the way information is structured. We are heading into this unit where we start to build geometric proofs for the very first time. So when we think about a proof, we're looking at a logical argument using deductive reasoning. And deductive reasoning is building off of information that we know is true. We're building off of facts, established truths. When we justify our statements, we cite things that we already know to be true. We cite properties, we cite definitions, postulates, and theorems. So in geometric proofs, right, our goal is to explain why something works the way that it does. Okay, we see a lot of conditional statements. A conditional statement is an if-then statement. So we're taking a statement and just rewriting it in this structure. If our hypothesis, then our conclusion. Often we use the letters P for hypothesis and Q for our conclusion. So when we're looking at our logical notation, if we're writing things shorthand, we're saying P implies Q. Our hypothesis implies our conclusion. Let me write that to the side. So P implies Q. Our hypothesis implies our conclusion. Okay, counterexamples. A counterexample is a specific example that shows a statement is false. So let's say that I give you this example. Let's say that I tell you, for example, all apples are green. Okay, so I'm giving you this statement, all apples are green. If I rewrote that in conditional form, I would say something like, if it is an apple, then it is green. If I'm trying to come up with a counterexample, I'm looking for a specific type of apple that is not green. So I'm going to say, well, this statement is false, and it's false because I can come up with a counterexample of red or maybe yellow apples. Okay, so again, looking at my statement, all apples are green, as a conditional, it would be, if it's an apple, then it is green. I'm saying, oh, I know that that statement is false. Here's a specific example to show you why. We know that there are other types of apples that are not green, right? Such as a red apple, such as a yellow apple. All right, example one, we start off very basic. Can you transform each statement into a conditional? So we're saying, can you rewrite it as an if-then statement? So here I'm saying high heels are shoes. So I'm essentially giving you the hypothesis here, high heels, and shoes as the conclusion. So something like this, I would say, if they are high heels, then they are shoes. Now you may notice that I'm using a few extra filler words. That's fine. I really need to see something with the if next to the high heels. That's your hypothesis. The then should be next to the shoes. That's your conclusion. If you add a few extra filler words just to help you make it make grammatical sense, that is fine. So the implication here is that high heels belong to this broader category of shoes. Sometimes we show this as an Euler diagram. I'll illustrate that for you one time. So here I have a rectangle with a circle inside. So the circle is meant to be your hypothesis. So here I'll put, my high heels, right? High heels, just abbreviating, belonging to this broader category of shoes. Right? And that makes sense because our high heels do belong to the broader category of shoes. Our high heels right here, that's the hypothesis, that's in the circle. And then here in that rectangle, this is shoes. And this is an Euler diagram. All right, so you spell Euler as E-U-L-E-R, diagram. All right, another example, linear pairs are supplementary. So using some geometry vocabulary. So if angles form a linear pair, then they are supplementary, right? That would be an example of what this looks like as a conditional. So if angles form a linear pair, then they are supplementary. Okay, so here again, just another example that works out to be true, right? Linear pairs are always supplementary. So if I drew that as an Euler diagram, I would have linear pairs in my circle, supplementary angles in my rectangle, which implies that linear pairs would belong to this broader category of supplementary angles. All right, next thing to go over is this idea of a negation. So a negation is the opposite of the original statement, not P. This is the notation to negate P right here. So for example, here I'm saying, can you write the negation of each statement? So if I say the car is white, right, then my negation would be to say the car is not white. And I'm just saying the exact opposite thing. If I give you a statement, it is not snowing, the opposite of that is to say, well, it is snowing. So again, to negate something is to say the exact opposite statement. All right, next up, we're looking at related conditional statements. We've already talked about a conditional. So remember that we think of P as our hypothesis. Q is our conclusion. Okay, so the original conditional is saying, well, if P, then Q. Right? P implies Q. In symbols, if I'm trying to convey that shorthand, P with an arrow to Q. Okay, the converse, what I do with the converse is I just reverse this statement. I say it in the opposite direction. So I say, if Q, then P. Right? My conclusion implies the hypothesis. Q with an arrow to P, right? I'm literally swapping the hypothesis and the conclusion of the original conditional. Okay, for an inverse, we negate the conditional. So I'm saying if not P, then not Q. So again, the inverse negates the original conditional. In symbols in shorthand, I would say not P to not Q, just like that. Okay, the last one is the contrapositive. And the contrapositive, we negate the converse. So if not Q, then not P. So not Q to not P. All right, one more time. The conditional is our original if-then statement. P implies Q. The converse, we swap the hypothesis and the conclusion. We swap the P and the Q. We go in the opposite direction, Q to P. The inverse, we negate the original conditional. And for the contrapositive, we negate the converse right here. Let's do it with an example right here. All right, so here I'm saying let the hypothesis be, you are in New York City. Q, the conclusion is you are in the USA. Write each statement in words and notation and decide whether it's true or false. If it's false, provide a counter example. So our conditional statement, again, that's P to Q if I'm thinking of my fancy notation. I would say something like, if you are in New York City, then you are in the USA. And that makes sense. That's true, right? If you're anywhere within New York City, you are absolutely also in the USA. That is true. Okay, the converse here, we reverse it. Q with an arrow to P. So here I would say something like, if you are in the USA, then you are in New York City. Okay, well, that's not true, right? That's false. That's false because I can think of a place in the USA that's not New York City. So here I'm going to say false, and then I can provide a counterexample. So maybe my counterexample here is San Francisco. Right, so I'm thinking of a place that is in the USA that is not New York City. So San Francisco, great counterexample, right? We're saying that it's a truthful hypothesis, but a faulty conclusion over here. So a place that's in the US, not New York City. San Francisco does the job. All right, inverse. Inverse, we are negating the original conditional. So not P to not Q. If you are not in New York City, then you are not in the USA. Okay, well, that's also false, right? That's a false statement. So I'm trying to think of a place that is not New York City, but is in the USA, right? And I can find an example of that, right? So this statement is not true because I can say, I can think of a place that's not New York City, but is in the USA. My counterexample could be Los Angeles. All it takes is one counterexample to show why a statement is not true. All right, the contrapositive. We're negating the converse, not Q to not P. So here I'm saying, if you are not in the USA, then you are not in New York City. Okay, so think about that for a moment. If you are not in the USA, then you are not in New York City. Well, that's true, right? I can't think of a counterexample to show why that statement is false. This is absolutely true. Now, one thing that I want you to notice, and I'm going to formalize this when I look at the other side of the page, is that your conditional and the contrapositive, right here and here, will always be the same. They're going to always both be true or both be false. They're going to go hand in hand. In this case, they're both true. And then same thing here, your converse and your inverse, they're going to always be both true or both false. In this instance, we're seeing that they're both false. We came up with a counterexample to show why they're false. All right, let's flip it over to the back. All right, so here, case in point, right, I'm just illustrating what I just said. A conditional statement and its contrapositive are either both true or both false. The converse and inverse of a conditional statement are either both true or both false as well. All right, moving on. Definition. We call a statement a definition if both the conditional and its converse are true. We're saying that something works in both directions, P to Q and Q to P. It's a true statement in both directions. And when it is a definition, we can structure it in biconditional form. So here we're seeing this double arrow, P to Q, Q to P, right? We're implying that it's true in both directions. And the way that we structure that is we say our hypothesis P, if and only if our conclusion, which is the Q. So let's do an example. So example 4. All right angles are 90 degrees. Is this a definition? Let's start there. Is it a definition? Well, let's think about it as a conditional. If it is a right angle, then it has a measure of 90 degrees. Is that true? Yes, the conditional is true. Let's go in reverse and think of its converse. If an angle has a measure of 90 degrees, then it's a right angle. Is that still true? Yes, still true. It's true in both directions. So we'd say yes. It is a definition because the conditional and its converse are true. And when we can say that it's a definition, then we can rewrite it in biconditional form. So we can say it is a right angle if and only if it has a measure of 90 degrees. Okay, so a statement is a definition if it's true in both directions, if the original conditional and its converse are both true. And when it's a definition, we can rewrite this in biconditional form. We take the hypothesis, it is a right angle. If and only if, then the conclusion, it has a measure of 90 degrees. All right, next up, example 5. I'm giving you a diagram. And I'm saying, are these statements true? Tell me why. So here in A, I'm saying measure of angle AEB right here is 90. Is that true? Well, yeah, that has to be true. I see this right angle notation here. That tells me that these pathways run perpendicular. That means that all of these angles here have to be 90 degrees. So I'm going to say true. Maybe my explanation is just that those pathways run perpendicular. Perpendicular pathways create the right angles, right? All of these angles would be 90 degrees. Okay, for B, points A, C, and D are collinear. Well, that's false, right? Collinear means they're points on the same line, right? We see that word line built into it. So here we're going to say false. All 3 of these points are non-collinear. A and C are collinear, but not with D. Okay, for C, I'm saying AC. So here's ray AC, and then ray CA are opposite rays. Well, that's false. They do extend in opposite directions, but they need to have the same endpoint. So here I'm going to say false. We need the same endpoint to have opposite rays. So for example, we could have used EA opposite EC. Those would be opposite rays. Okay, next we're looking at this idea of a logical chain. And here all we're doing is we're organizing statements. We're linking them together in proper order. So an example here, I'm saying let's put the statements in order to form a proper logical chain, then write the resulting conditional. So we have these 3 statements. We have if there's a parade, then fireworks will go off. If it is July, then flags are flying. If flags are flying, then there is a parade. So you're looking for the statement that starts things off. Look for the conditional statement where there's a hypothesis that's not mentioned in any conclusion. And that would be right here where B is. If it is July, there's no mention of July in any of those conclusions. So we must start with B, if it is July. So if it's July, then flags are flying. We start with B. Okay, then we mentioned flags are flying. So we pick up here. If flags are flying, then there's a parade. So B to C. We close out with A. If there's a parade, then fireworks will go off. So again, we look for the first conditional statement and the hypothesis where there's no mention in any of those conclusions. And that starts things off. And then it's pretty easy to see how they connect. If it's July, then flags are flying. If flags are flying, then there's a parade. If there's a parade, then fireworks will go off. And the resulting conditional is taking that original hypothesis and joining it with the final conclusion right here. So if it is July, then fireworks will go off. So again, the original hypothesis with the final conclusion. Okay, lastly, just a quick talk about different types of reasoning. So first, we're looking at inductive reasoning. So inductive reasoning is a bottom-up approach, works from specific to general. That's the big thing that I look for, specific to general. Arguments are typically based on experience or observation. For deductive, it's more of a top-down approach, works from general to specific. Arguments are typically based on laws, rules, or other accepted principles. This is the type of reasoning that we're going to use when we build our geometric proofs. We're trying to build off of facts, things that we've established as true. I'm going to add that word here, facts. We're building off of prior knowledge, things that we know to be true. All right, so going through example 7, determine whether the reasoning is inductive or deductive. Each time you forget to do your math homework, your parents take away your phone privileges for a day. So the next time that you forget to do your math homework, you will lose your phone privileges. Okay, so here it is taking us from something specific to general, and it's definitely based on experience, personal experience. So this one I would say is inductive. Again, specific to general, or thinking that this is essentially establishing a pattern. It's based on experience. Okay, next one, B. If you live in Nevada, you're between the ages of 16 and 18, then you must take driver's ed to get your license. Well, that feels pretty general to me. Marcus, he lives in Nevada. He's 16 years old. He has his driver's license. Therefore, Marcus took driver's ed. So here we're definitely going from general to specific, right? We're basing it on established rules and laws. So here we would say deductive. Right? You could say rules, laws, or you could say it looks like it's general to specific. Okay. For C, for the past 3 Wednesdays, the cafeteria has served mac and cheese for lunch. Dana concludes that the cafeteria will serve mac and cheese for lunch this Wednesday. So here again, we're starting pretty specific based on someone's experience. And then here, Dana concludes that this Wednesday, they're going to serve mac and cheese. So this is, again, inductive. We could say pattern, experience. Or we could argue it's going from something specific to more general. Okay, the last one. A number can be written as a repeating decimal if it is rational. Pi cannot be written as a repeating decimal. Therefore, pi is not rational. So here we're starting off with something that is general, building to something more specific, right? We're looking at something that's more concrete based on established facts. So this one is deductive. So again, you could write general to specific. That's our big identifier. Okay, or think of it as our argument is based on established rules or facts. That's what makes it deductive. All right, have a good rest of your day, you guys.